Hello everyone. Today we're going to be doing lab 6, which is the aldol condensation. So the reaction that we're going to do is we are going to combine benzaldehyde as well as acetone, which is the exact same thing that we just clean everything with. And we're going to do the only 2-to-1 reaction in the entire course. So pay attention to that when you're calculating your percent yields. That is, 2 benzaldehydes are combining with 1 acetone to make a single dibenzalacetone product. I'm not going to get into the mechanism right now. I'm actually just going to jump straight into the procedure. So this whole thing is actually just a hand-shook reaction because it occurs rather quickly. In this 40 ml screw top vial, I have 0.75 milliliters of benzaldehyde. To this, I'm going to add 0.3 mils of acetone. I've got everything else pre-measured, but acetone is both volatile and it eats this type of plastic, so I'm going to move this pretty quickly. Acetone is in, and next I have some 95% ethanol. And lastly, this is our aldol catalyst solution, which is potassium hydroxide, which is our basic catalyst, dissolved in a mixture of ethanol and water. 3 mils of that going in. Now, this reaction, notoriously, as we've learned throughout the years, does release quite a bit of gas as it proceeds. And so what I'm doing right now is I'm just swirling it open top to allow some of that gas to escape before I put the cap back on and shake it. What I'm expecting to happen is this should turn from clear to yellow color, and then eventually kind of a pleasant peach color. It's going to be nice. We're already getting a little bit of yellow coloration in this. And now I'm going to go ahead and get the cap on. And I'm going to shake like this. And about every minute or so, I'm going to vent this. And it's going to stay nice and boring because we're venting so often the pressure is not allowed to build up. Shaky, shaky, shaky. And maybe you can see that yellow color start to develop there. Turning more of a peach color now. Now, after a few minutes of this, I actually expect the solid to start forming. And because if you look at the structure of the product, it's really, really non-polar. Not only is it symmetrical, but it's got those 2 giant benzene rings attached to it. This solution that we're working in is water for some part. And the presence of water in the solvent system is going to make the really, really non-polar product precipitate out. And so you can see it's gone from clear, and I've got some chunky stuff up on the sides of my container, as well as this is getting all cloudy. So that's my solid that I'm collecting. So the product is mostly made by now. I'm just going to shake it a little bit more. In order to collect this solid and get it away from the liquid, I'm going to use vacuum filtration, more specifically a Buchner funnel. Okay, give me one more. That good. My gloves actually got a little bit wet because as pressure built up along the rim of my container, the liquid pushed itself out, and so I'm going to swap gloves very quickly. But you can see how cloudy that's gotten and how the sides of my container are actually plastered with solids. Clean gloves. So after the shaking has been done, I am going to go ahead and I've got ice water already ready over here. Is my funnel in the shot right now? Can we see this on the camera? Thank you. So here is my vacuum filtration setup. I've got a piece of filter paper which I've already weighed, so that later on I can just weigh the dry product on top of it. That's going to go in, and I'm going to go ahead and turn on the vacuum. It sucks down the paper. And just hit this with a bit of ice water. And now it's wet and it sucks down, so there's very little chance of any solid escaping down and out the bottom of my filter paper. And so now I'm going to dump all of this just straight on top. Ooh, it's sludgy. And there is a ton left in here, so I'm going to use ice water to go ahead and collect this. And again, this product is super non-polar. So if it didn't dissolve in normal temperature water, it definitely is not going to dissolve into this ice water. Alright, I'm happy with this. Alrighty. So, I've got all of my products over there, and it's still wet and drying in my funnel. And I'm just going to dribble some ice water across all of my product. And again, the product isn't going to dissolve in ice water. So it's going to stay up on top of the paper. And all the contaminants, things that I want to remove anyway, those may dissolve in the water and fall through. Okay. So at this time, we're going to allow the product to dry on the funnel. In order to speed up the drying process, I'm just going to take a spatula and I'm going to bend it at a 90-degree angle like this, and I'm going to smash this out flat, because if you've got a big clump of solid, the inside, the center of it is not going to dry. But if you have a nice full area where air is passing through all of the surface, that all is going to dry evenly. Smash, smash. It has the texture of, like, I'd say Play-Doh mixed with glitter. All right. And with that being said, I'm going going to go ahead and let that dry for several minutes, and we'll get back to that once it's dry. When we just cut, we were drying our crude dibenzilidinaseton product on a vapor funnel. That dried for probably about 15 minutes, and I smashed it flat a couple of times just to make sure that it was drying evenly. And what I got as a product was this flaky, pasty solid, bright yellow. You can see that a lot of that red coloration that we saw in the reaction is gone by now. That went and washed away in the filtration step. So the mass of our crude product here is 0.4403 grams. With our conversion factor to figure out how much ethanol we need to recrystallize our product, our conversion factor is for every 0.4 grams of solid, we need 1 milliliter of ethanol. So go ahead and figure out how much ethanol I'm going to need to do my recrystallization. Okay. So the amount of ethanol that I need is approximately 1.1 milliliters. At least that's the best that I can measure with the tools available. So I'm actually just going to use a syringe for this and pull straight from this ethanol squirt bottle. So there's 1 mil. And let's get another 0.1 mil in there as well. Okay. So now we are going to move on, and you can see that it is not dissolving at all in the ethanol at room temperature. This amount of ethanol should only dissolve my product at full reflux temperatures. So I have a preheated hot plate over here at 100 degrees Celsius. And if I start heating this up and intermittently agitating, then I expect all of that solid to dissolve and it will be completely homogeneous and clear. So after I see that, and after I'm at a full reflux where I can see some dribbles, some drops of ethanol running down the sides of the glass, then I can put my reaction flask into a clamp, and hanging up in the air will be the slowest way for us to cool that down. And when you are doing a recrystallization like this, the slower you cool it, the more pure your product will be. Okay, so about 5 minutes have passed, and what I see now is that I have a gentle reflux, just a gentle boiling happening over here in my recrystallization. And also, let's see if I can bring this over here well. This is completely translucent, so that cloudiness, the product and the solid, has all been dissolved into solution. So this is the perfect starting point to do a recrystallization in. So I'm going to go ahead and clamp it in the air. I'm going to give it a wiggle because recrystallizations love to just fall when you're not looking. So this is really nicely clamped. So this is going to cool at room temperature. It's going to take probably 2 or 3 minutes. Something that's kind of interesting to compare it to, water has a crazy high specific heat, whereas ethanol does not, meaning that ethanol cools much, much faster than water. All right, so we're back after about 10 or 15 minutes, and this has been cooled completely to room temperature. And what I hope you guys can see is that not only has solid appeared, it may be more difficult to see, but it's actually very angular and sharp and pointy crystals. That sharpness and that pointiness and the glossiness of the crystals is a great indicator that our crystallization has worked. That's a great visual indicator that we have crystals and not, as opposed to that, a precipitate, which forms very quickly, doesn't help with purifying anything, and just looks like a sandy, opaque solid. Moving on. We are going to use a beaker funnel to collect these purified crystals. So I'm going to turn that on. Making sure that my paper is stuck down onto the funnel with a little bit of ice cold ethanol. And this is just so solid and chunky. I'm going to go ahead and scoop it out at first with a little bit of spatula there. Try to keep it cold. And let's collect. And a ton of it is left over. I'm going to get out what I can with a spatula. And then just use a few portions of ice cold ethanol to try to collect as much as I can. And you can always, to cool things down, just dip it in the ice bath. That room temperature cooling took forever because it was just through air. But by using ice water, we can very quickly cool things down this way. One more. Just use the rest of my ethanol here. Ta-da! Okay. So over here we have our crystals, which are sucked up against our paper. Ethanol is going to dry pretty quickly, which is the main component of the solvent here. These crystals are really shiny and flaky and beautiful, and I'm going to ruin that completely by smashing them with a spatula, increasing the surface area, and forming a fine powder that's going to dry really, really well. I'm going to go ahead and crank my vacuum, and this is actually going to be dry within about 10 seconds. A very common question I get when we're doing labs that involve beaker funnels is, how do I know if my solid's dry? So the best indicators are that you can pick up your powdered solid and it falls off the spatula without sticking to it at all. Great indicator there. Also, I'm looking at the color and the appearance of the filter paper underneath. If the filter paper's wet, there's still more liquid to remove from the system. If filter paper looks dry and opaque, just like when it started, that's how you know your solid on top is probably dry as well. Okay, so this is completely dry. And I'm just going to bring it over to the camera and show you guys. So this is the appearance of my products, my Dibenzilidinaseton. And it's very flaky, it's very shiny, even though I've smashed it because it is rather purified and crystalline. And so what I would hypothesize is that if I took melting points of my crude material earlier, which I saved a little melting point sample of, as well as this recrystallized product, I would expect this to have a higher and sharper melting point, which is closer to the literature value, as opposed to the crude stuff, which I would probably assume has a depression of 10 or 15 degrees and a much broader melting point. So we are going to take all of that characterization along with a mass of the product so that you can calculate the yield from this, and send that to you guys with this video.